Okay, so for this problem, I'm using the GeoGebra geometry calculator to think through what's going on. Desmos is great for a lot of things, and in fact, I'll probably use it later, but for right now, just visualizing this geometric problem, I think GeoGebra does a great job. So I'm going to start by looking at our problem. So a problem is um, if we place points on this circle and connect them with a chord, how many regions do we get? In particular, what is the maximum number of regions that we get? And so you can see that when I have 2 points, I have 2 regions. So let's do n points and then our regions. When I had 1 point, there isn't any chords, so we just have 1 regions. Now that we have 2 points, we have 2 regions. If I go ahead and add a third point, if I add another point, and our goal is to figure out, if I have any number of points, how many regions am I going to have? And there seems like a pretty obvious pattern so far. So right now, we're doubling every time. I'm going to go ahead and spoil it and say this pattern doesn't hold. So I want to talk you through just my approach to when I thought about this problem and was solving it for the first time. It is not necessarily the most efficient way to solve the problem. So the first thing that I thought about was, okay, what happens every time I add a new point? So I'm going to go ahead and add a point and talk about what happens. So I looked at this as what happens when I connect this point to the points that were already there. So now we're on case 5, we have 5 points here, and we're trying to figure out how many regions are we going to end up with. So I thought about this as, okay, what happens when I connect to the existing points? So I made up a word here that I call the adjacentness of the point. And by that, what I mean is how far away the other points are from the point we just drew. So this point here, that's our new point. And then this one is the point that is adjacent to it. So I gave this point an adjacentness of 1. This point is now 2 away, so I gave it an adjacentness of 2. Again, that's a word that I made up to describe this. If you know a better word for it, or like an actual word, an existing word, let me know. I'd be curious to know if there is a word for that. So, okay, so when I have an adjacentness of 1, meaning I am actually adjacent, I'm just 1 away from my new point. When I connect that line, I don't have to cross any other lines, so I just end up with 1 more region than I had. Then, when I have an adjacentness of 2, here I cross 2 lines, and that creates 3 new regions. But why does it cross 2 new lines? Because that number actually does end up changing as it goes from one figure to the next. So I might look at that one that's 2 away and say, okay, it crosses 2 lines, it creates 3 new regions. And that number, we are at figure 5, or we've got 5 points here. So I might consider that n minus 2. So I have 5 points. And if I subtract 2, I get 3, which is my 3 new regions. So that might be a pattern that works. But let's try to think about why that would be the case. So if I look here, this point, it has 4 lines that are coming off of it. And it has 4 lines because it connects to all 4 of the other points. It just can't connect to itself. So the number of lines that extend from a point on our circle is always going to be n minus 1. Because it would be n if it could connect to itself, but that doesn't draw a new line. So it's n minus 1. Now, I'm not going to cross all of those lines when I draw a new line. So I don't cross either of those 2 lines when I'm at this adjacentness of 2. So how does this help me decide that this is going to hold true the entire time? Well, it's going to hold true because I've got n minus 1 lines that I could cross, but I don't cross 2 of them. And I know I'm never going to cross these 2 when I'm drawing the line from our new point to the one that's 2 away from it, because there's always going to be those 2 lines highlighted in orange that I don't cross. So I'm not going to cross 2 of those lines. So this is the number of lines I cross. The number of lines I cross is not equal to the number of regions created. Instead, if you think about like, if you were dividing up a rectangle, if I draw 2 lines, I've cut it up into 3 pieces. The same sort of logic is happening here with the number of lines I cross. If I'm crossing 2 lines, then I end up creating 3 new regions. So the number of regions is always 1 more than the number of lines I cross. So we end up there with that n minus 2. That is always going to be true. Okay, and now we've connected all of our points. So how many total new regions do we have? Well, we have our 8 that we already had. We have these 2 points have an adjacentness of 1. So for each of those points, we have 1 new region. So we have 1 new region. We have 2 of those points. Then we also have 2 points that have an adjacentness of 2. They're 2 away. And so my n is 5 here. So 5 minus 2 is going to give me 3. So that's our 3 new regions we were seeing on each side there. So we're going to have 3 new regions for each of those points that have an adjacentness of 2. So all together, that means I'm going to have 2 plus 6 more, which is 8 more, which gives me a new total of 16. So I'll go ahead and add a point here. And now I want to talk a little bit real fast about where we're placing our points and the fact that this problem is asking us for the maximum number of regions. So if I have a point out here, there's this triangle region that we can see. But if I move my point here, that region goes away. So it's important that we are defining this problem with the maximum number of regions. So we're going to place our point so that this doesn't occur. We never want to have 3 lines intersecting at one point. Every point should have only 2 lines intersecting in order for us to have the maximum number of regions that we count. So if we ever see those 3 lines intersecting, we want to move our point. But I'm not going to start actually with this segment. I'm going to see if the patterns we already had were holding. So I have 2 points with an adjacentness of 1. Each of those add 1 new region. So we had 2 points with an adjacentness of 1. Now I'll go ahead and go to my adjacentness of 2. And let's just double check how many lines we cross. So with this formula being n minus 2, and we're on our 6th point, that should be 6 minus 2 is 4. So if this holds true like it should, because we're not crossing either of these 2 lines, we should cross 3 lines for a total of 4 new regions. So we have 1, 2, 3 lines that we cross there. 4 new regions being created. And that is also going to happen on our other side. We go our other direction. And again, 4 new regions being created. So there we have 4 new regions times 2 points with that adjacentness of 2. Now we have a new number that we hadn't gotten to yet. That is our adjacentness of 3. So when I draw the line there, let's see what happens. So I've drawn my line. We don't have any of those intersections of 3, so we're good with where that point is. So how many lines do we cross? This point has n minus 1 lines coming off of it, but we're not going to cross all of those lines. The lines that we don't cross these 3 orange lines. So we don't cross 3 lines. So we cross n minus, so there's n minus 1 lines and 3 that we don't cross. So we cross n minus 4 lines. And this doesn't just happen at this point, it also happens at this point. So we will again cross these 2 lines, but we will not cross these lines. So this happens twice for a total of 2n minus 8 lines crossed. But remember, that's not the number of regions. Our number of regions that we create, if we cross 2 lines, we create 3 regions, right? So if we cross 2n minus 8, we need to add 1 to figure out how many regions we're going to create. It's going to be 2n minus 7 new regions. So in this case, if we're on point 6, which we are, like it shows here, we've added our 6 point. So 2 times 6 is 12 minus 7 is 5. So we should create 5 new regions. And if we count 1, 2, 3, we cross 4 lines, just like we'd expect. So we do create those 5 new regions. And there's only 1 point that has an adjacency of 3. So we only do that 1 time. So we have 5 new regions created once. So if I add all of this up, we end up adding 15 new regions for a total of 31. And you'll see that doubling pattern breaks. And if you don't believe me, you're like, I don't know, I'm not convinced that there's not 32 here. We'll go ahead and just count all of these. And there you have it, 31 regions. So let's go ahead and start our new problem. We'll put a new point on there. We've got a pattern for 1 away. We've got a pattern for 2 away. We've got a pattern for 3 away. So we can actually solve this problem because the farthest away any of the points are is 3. So let's go ahead and just use the pattern that we've generated so far. So there are 1 new region generated twice. That's happening here. Those are both 1 away. Then we're on n equals 7. 7 minus 2 is 5. 5 new regions are generated twice. And again, we're on n equals 7. So that's 14 minus 7, which is 7. And there are 2 points that are 3 away. So we're going to generate 7 twice to give us a grand total of 26 new regions that we're adding to our previous one, which gives us 57. And I'll go ahead and fill this in. So let's try our next case. So again, we still have that adjacentness of 1. We still have that adjacentness of 2. We've got patterns for all those. We've got our 3 here. And now we have one that is 4 away. So I already started noticing some patterns that are true for every point. So every point that we're going to cross has n minus 1 lines extending from it, because that is how many points we can connect to. The lines that we don't cross include So the lines that we don't cross include the line connecting to our new point and the lines connecting to the points in between this one and the one we're connecting to. We don't cross the line that connects us to our new point or to the points leading up to this one that we've just drawn, our newest line, basically. So this is an adjacency of 4. So there is 4 points that um, 4 lines that we're not connecting to, because these are essentially the lines that are on the in-between. Could think about how I think about this right now is there's like 4 points away from our new one that we're not connecting to. And we're already excluding the one that connects to itself. So basically just this whole, everything on this arc, the lines that connect to those points, we're never going to be crossing with our new one because they're just hidden to the side, basically, compared to the one that we are crossing. We aren't ever going to cross whatever our adjacent number is of lines. So the total lines that we don't cross is n minus 1 minus a. And then this is going to repeat for each of the points in between. So that's going to repeat for whatever our adjacentness is, minus 1. We're going to do that 3 times. So I'm going to go ahead and multiply this out. I mean, we could leave it here and just say, hey, that's our formula. But I am going to multiply it out so we can sort of see it more in this structure. So if I distribute the a, I get an minus a squared. If I distribute the negative 1, I get minus n plus 1 plus a. So I want to end up with all my n's grouped together and just some constant. So I'm going to reorganize this to an minus n. This negative a and this positive a cancel out. So minus a squared plus 1. And then I'm going to factor out the n here. So we're going to have a minus 1 times n minus a squared plus 1 as our general formula. So we're going to see if that works. So let's try that for our adjacentness of 3. If I plug in 3 for a, then I end up 3 minus 1 is 2 times n, and then that would be negative 9 plus 1 is negative 8. Oh, this was all about the lines we were crossing, and I forgot I need to add 1 to give me the number of new regions. So instead of plus 1 there, that should be plus 2 for the number of regions. So this formula is the number of lines I cross. 1 more than that is going to be the number of new regions that is created. So again, checking with our adjacentness of 3, that gives us 3 minus 1 is 2n. Minus 9 plus 2 is 2n minus 7. So that checks out. If we try that now for 4, because that's our new one here, that should give us 3n. 4 squared is 16. So minus 16 plus 2 is going to be minus 14. So let's go ahead, actually figure out what that number is for our current n value. So now we're on 8. 8 points are on this circle. So if I plug in 8, 3 times 8 minus 14 is 24 minus 14, which is 10. So that tells me 10 new regions should be created, or in other words, 9 total lines should be crossed. So 1, 2, 3, 4, 5, 6, 7, 8 9. So 9 lines were crossed, which means 10 new regions just got created by drawing that line, just like we were expecting. Well, let's go ahead and finish this problem. Okay, so let's go ahead and actually fill in our table for our 8 points. So we had 57 regions already. What are we going to add? So we've got 2 that are 1 away, creating 1 new region each. We've got 2 that are 2 away. If we are on 8, 8 minus 2 is 6. So they're each creating 6 new regions. So then we've got 2 that are 3 away. Each of those are creating 16 minus 7 is 9 new regions. We've already got those 10 new regions coming from this 1 point. So all together, that's going to give us 2 plus 12 plus 18 plus 10 new regions, which is 42 new regions. So if I add that up, I'm going to end up with 99 regions here. Okay, so we've got a pattern, and now we can pretty straightforward do this recursively, meaning I can always figure out my next one pretty easily. But what I'd rather do is be able to jump to, like I said, 10 or 100 or 50, 500. So how can we figure out a general formula for this? Something that doesn't require me to know the previous number of regions. So I'm going to go ahead, scoot this over, and look at this pattern a little bit more. So we know that we're not doubling every time. And another really common way to look at function families is by looking at their rates of change. So for example, if I have something linear, that would mean I'm adding the same amount every time. So the change is 2 there. So linear looks like the classic y equals mx plus b. In other words, it just is something where it has an x in it. On the other hand, if I have something that is quadratic, in other words, it has a degree of 2, it actually has a rate of change that is linear. So its rate of change goes up by a constant amount every time. So this sort of pattern keeps continuing. So something with a degree of 2 has something with a degree of 1 as its rate of change. Or in other words, the rate of change becomes constant once I get 2 out. So we call this our first difference, and this one our second difference is constant. So figuring out what difference we end up getting a constant can tell us what degree polynomial will model this. So if I keep going here, this right here is not linear yet because it's not increasing by the same amount every time. So we're going to keep going until we get that constant difference. And here we go. So there we go. It took us 4 differences to get to constant. So this, a 4th difference being constant, tells us that this function is going to be modeled by a 4th degree polynomial. Now, this is just sort of an observation. We can't 100% guarantee by just looking at the numbers that we have so far that the next one is going to hold this pattern. Just like when we saw it doubling up to here, we could have been really confident that it was doubling. We had 5 data points for it, but then it broke. So how can we know for sure, given properties of our circle that we're working with, that it's going to continue following this pattern and end up with a fourth degree polynomial. In other words, the word for that is a quartic polynomial. So something that looks like, and I'm going to use f because I don't like using e as a variable because of the mathematical constant, Euler's constant e. So I'm predicting that we're going to have something that looks like this. However, how do we know that that's going to be? How do we know that that's going to be the case? We want to try to convince ourselves based on the properties of the circle more than just looking at some numbers.